Tonight, we're going to travel to the edge of everything you think you know about the universe, and then a little further beyond that. Not to the edge of a galaxy, not to the edge of the observable cosmos, but to the edge of a question so vast, so quietly terrifying, that most people spend their entire lives never looking directly at it. Tonight, you and I are going to look at it together. We're going to sit with it, and by the end of tonight you're going to understand exactly why the universe is expanding, what is driving it outward into the dark, and why that answer, the real answer, the one buried beneath the textbooks and the diagrams, should fill you with equal measures of wonder and awe and a very particular kind of dread. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a fact about the universe that most people have heard, but very few have truly felt. Not understood in the way you understand a math equation or a news headline, felt in the chest, in the quiet part of the mind that wakes up at 3 in the morning and stares at the ceiling. It is a fact so enormous, so relentlessly strange, that even the scientists who have spent their entire lives studying it admit they do not fully know what it means. And tonight, you and I are going to sit with that fact together. We are going to let it breathe. We are going to follow it all the way to the edge. The fact is this: the universe is expanding. Right now, in this moment, as you lie here in the dark, as your breathing slows and the world outside your window grows quiet, the universe is growing. Every galaxy is moving away from every other galaxy. The fabric of space itself is stretching outward in every direction, carrying everything with it, like dots drawn on the surface of a balloon being slowly, steadily, endlessly inflated. This has been happening for 13.8 billion years. And here is the part that most people do not stop to absorb. It is not slowing down, it is speeding up. Something is pushing the universe apart. Something invisible. Something with no name that fully satisfies the physicists who study it. Something that makes up 68% of everything that exists, and yet has never been directly detected, touched, or explained. We call it dark energy because we needed to call it something. Because the alternative was admitting that the majority of the universe is made of a force we do not understand, driving a process we cannot stop, toward an ending we can barely imagine. And that, quietly, is exactly what is true. Tonight we are going to travel through that truth slowly. There is no rush. The universe has been expanding for billions of years before you were born, and it will keep expanding long after every star in the sky has burned to ash and gone cold. We have time. We have the whole night. And what I want to do, more than explain the science to you, is help you feel the scale of it. Because the scale is where the real experience lives. Not in the equations, not in the diagrams, but in the moment when a number becomes so large it stops being a number and starts being something closer to a feeling. Let me start with something simple, something close, something you can almost touch. Think about the sun. You know the sun. You've seen it your whole life. That familiar burning disk that rises every morning and sets every evening and makes the whole world warm. The sun is about 93 million miles away from where you're lying right now. That sounds far, and it is far. If you drove a car at highway speed without stopping, day and night, through the vacuum of space, it would take you roughly 177 years to reach it. 177 years of driving, just to reach our own star, just to reach the nearest thing we have to a home in the cosmos beyond Earth itself. Now hold that number, 93 million miles. Hold it in your mind and let it feel large, because I am about to make it feel very, very small. The nearest star to our Sun is a system called Alpha Centauri. It is approximately 25 trillion miles away. 25 trillion. That same car, driving at highway speed without stopping, would need roughly 30 million years to get there. 30 million years of driving just to reach the next star over, the next light in the sky, the nearest neighbour in a galaxy of 300 billion stars, and our galaxy, the Milky Way, is just one galaxy. One island of stars in a universe that contains an estimated 2 trillion galaxies. 2 trillion. Some of those galaxies are close enough in cosmic terms that we can resolve their spiral arms with our telescopes. Others are so far away that the light reaching our eyes right now left those galaxies before the Earth even existed. before the sun had formed, before the solar system was anything more than a slow spiral of gas and dust drifting in the dark. You're looking back in time every time you look up at the sky. Every single star you see is a message from the past. Some of those messages are thousands of years old, some are millions, and some, from the farthest reaches of the observable universe, are nearly 14 billion years old. Here is the thing most people do not realize. When we say the universe is expanding, we do not mean that galaxies are flying outward through space the way a cannonball flies through air. We mean that space itself is growing. The distance between things is increasing, not because the things are moving through space, but because the space between them is stretching. It is a subtle but terrifying distinction, because it means there is no center, there is no edge, there is no single point from which everything is flying away. From anywhere in the universe, everything else appears to be receding. From any galaxy, in any direction, the cosmos looks the same. Everything running away, faster and faster, into an expanding dark. And that darkness is growing. Right now, as you breathe, as the room around you stays perfectly still, galaxies that were once within reach of our telescopes are crossing a kind of horizon, a cosmic threshold beyond which they are moving away from us faster than the speed of light. Not because anything is travelling faster than light, but because there is so much space between us and them, and that space is expanding so rapidly that the light from those galaxies will never reach us again. They are gone, not destroyed, just permanently, irreversibly beyond contact, lost to the expansion of space itself. This is what we are going to explore tonight. This slow, relentless, accelerating, vanishing act. The force behind it, the physics beneath it, and the deeply human question of what it all means, not just for the universe, but for us. For the brief, fragile, improbable fact of our existence inside it. Because there is something extraordinary about the timing of all of this. We happen to live at the one moment in cosmic history when the universe is still populated with stars and galaxies and light, when there is still something to see, when curiosity still has objects to reach for. In the deep future, that will not be true. The sky will be empty, the stars will be gone, and whatever minds exist then, if any do, will look out into a perfect, eternal darkness, and have no way of knowing that any of this ever happened. But tonight, the stars are still there, and you are still here, and the universe is still expanding around you in every direction, carrying you with it, as it has always done, as it will always do. There is something both terrifying and quietly beautiful about that. Something worth sitting with in the dark before you sleep. So let us sit with it together. Let us go slowly. Let us begin. Step outside on a clear night and look up. Really look. Let your eyes adjust to the dark. Let the familiar shapes emerge, the constellations, the faint smear of the Milky Way if you're far enough from city lights, the occasional slow drift of a satellite crossing the black. It feels immediate, doesn't it? It feels like you're looking at something real and present, something happening right now, something that exists in the same moment you exist. The night sky feels like a window. But it is not a window. It is something much stranger than that. It is an archive, a vast layered record of the past, stretching back billions of years, displayed all at once above your head every single night. And almost none of what you see is where it appears to be. Here is the truth that the night sky hides in plain sight. Light travels fast, but it does not travel instantly. Nothing does. Even light, the fastest thing in the known universe, moving at approximately 186,000 miles per second, takes time to cross the distances of space. And space is so incomprehensibly large that even at that speed, the journey takes a very, very long time. The light entering your eyes right now, the light that makes those stars visible, left its source long before you were born. Some of it left before your grandparents were born. Some of it left before human beings existed at all. You're not seeing the stars as they are. You're seeing them as they were. Every single star in the sky is a message from the past, and the universe has been sending those messages for billions of years, most of them still travelling toward eyes that may not yet exist. Let me make this concrete. The star you probably know best after the sun is a bright one near the constellation Orion called Betelgeuse. When you look at Betelgeuse on a winter night, the light touching your eyes left that star roughly 700 years ago. 700 years. When that light began its journey toward you, the year was approximately 1323. The Black Death had not yet swept through Europe. The printing press had not been invented. The continents of North and South America were entirely unknown to European civilization. That light has been travelling through the vacuum of space for 7 centuries and had only just arrived. And here is the quietly unsettling part. We do not know if Betelgeuse still exists. It is a dying star, one that astronomers believe could explode as a supernova at almost any time in cosmic terms. It may have already exploded, the news just hasn't reached us yet. Now stretch that idea further, much further. The Andromeda Galaxy, our nearest large galactic neighbour, visible to the naked eye on dark nights as a faint smudge of light in the constellation of the same name, is approximately 2.5 million light-years away. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. At that time, our earliest ancestors, the genus Homo, was only just beginning to appear on the African continent. The first stone tools were being shaped. The light that carries Andromeda's image to your eye tonight began its journey before the human story had even started. It has been crossing the void ever since, patient and silent and impossibly fast, and it arrived in time for you to lie here in the dark and receive it. This is what astronomers mean when they talk about looking back in time. It is not a metaphor. It is a physical reality built into the structure of the universe. The further away something is, the older the image of it that we receive. Our telescopes are not just instruments of distance, they are instruments of time. When the James Webb Space Telescope captures light from galaxies at the edge of the observable universe, it is capturing light that has been travelling for over 13 billion years. It is showing us what the universe looked like when it was only a few 100 million years old, a cosmic infant. A universe without planets, without complex chemistry, without any of the structure we now take for granted. We are seeing the universe's own childhood, preserved in light, delivered to us across an abyss of time that the human mind was never built to comprehend. And here is where the expansion enters the picture and makes everything stranger. Because those distant galaxies are not just far away in the ordinary sense. They are far away in a way that is growing. While their ancient light has been travelling toward us all these billions of years, the galaxies themselves have continued moving. The universe has continued expanding. So the galaxy whose light we receive as being 2 billion light-years away is not 2 billion light-years away anymore. It is much further. By the time any signal we sent today reached them, they would be even further still. The universe is not a static picture. It is a moving, expanding, accelerating thing, and every image we have of it is already out of date the moment we receive it. This means that the universe you think you see does not exist, not in any precise sense. The night sky is a composite of thousands of different moments, layered on top of each other, each star and galaxy shown to you from a different point in the past, all of it arriving simultaneously to create the impression of a single, coherent, present sky. It is one of the most beautiful illusions in nature, and it is one of the most quietly disorienting facts in all of science. You're never looking at the universe as it is. You're always looking at it as it was, and the it that existed then is separated from the it that exists now by an expansion that has been running, without pause, for nearly 14 billion years. There is something I find deeply moving about this, even as it unsettles me. Every photon of starlight that reaches your eye has survived an unimaginable journey. It was born inside a star, produced in the violent nuclear furnace at its core, and then it spent thousands of years slowly working its way out through layers of dense stellar plasma before finally escaping into the vacuum of space. And then it travelled. For years, for centuries, for millions or billions of years, through the expanding dark, past other galaxies and clouds of gas and regions of nothingness so complete they have no description in human language, until finally, against all odds, it arrived here. At this planet, at this atmosphere, at the back of your eye, that single photon completed a journey of cosmic scale to bring you 1 pixel of starlight, and you received it without even trying. The night sky is lying to you, yes, but it is lying to you in the most generous way imaginable. It is giving you a window not just into space, but into time itself. It is showing you the history of the universe spread across the dark above your head, available every clear night, free of charge, requiring nothing more than a patch of dark sky. and a willingness to look up and wonder. And what it is quietly telling you, beneath all the beauty, is that the universe you inhabit is not a fixed and permanent backdrop. It is a dynamic, expanding, evolving thing that has been changing since the first instant of its existence and has not stopped changing for a single second since. The light you see is ancient. The universe it came from is not the universe that exists now. And the universe that exists now is already different from what it will be tomorrow. Everything is in motion. Everything is receding. The sky above you is a record of a journey that is still, quietly, relentlessly continuing. The year was 1929. The place was the Mount Wilson Observatory, perched high in the San Gabriel Mountains above what would one day become the sprawling, light-polluted city of Los Angeles. Up there, in the cold, dry air of the California hills, far enough from the valley below to see the sky with unusual clarity, a man named Edwin Hubble was doing something that no one had ever quite managed to do before. He was measuring the universe, not a piece of it, not a local sample, the whole thing, or at least he was trying to. And what he found in the process of trying would shatter the most fundamental assumption that scientists, philosophers, and human beings in general had carried for the entirety of recorded history. The assumption that the universe simply existed, that it was there, that it had always been there and would always be there, fixed and eternal, and essentially unchanged. Edwin Hubble proved that assumption wrong, and the universe has never looked the same since. To understand what Hubble did, you need to understand what the scientific world believed before him. In the early decades of the 20th century, the dominant view among astronomers was that the universe was static, permanent. It had no beginning and no end, no growth and no contraction. It simply was. Even Albert Einstein, whose general theory of relativity, published in 1915, actually predicted a dynamic universe, one that should be either expanding or contracting, found this conclusion so uncomfortable that he introduced a mathematical correction into his own equations specifically to cancel it out. He called it the cosmological constant. It was, by his own later admission, a fudge, a way of forcing the math to agree with what everyone already believed. The universe is not changing, the thinking went. It cannot be changing. Change implies a beginning, and a beginning raises questions that science was not ready to answer. Hubble's tool for dismantling this belief was something called the redshift. Here is how it works. You have probably heard of the Doppler effect in sound. When an ambulance is racing toward you, its siren sounds higher pitched than it actually is, because the sound waves are being compressed by the vehicle's approach. When the ambulance passes and moves away, the pitch drops because now the sound waves are being stretched out behind it. Light behaves in a similar way. When a source of light is moving away from you, its light waves get stretched. They shift toward the red end of the spectrum. Astronomers call this a redshift. And when Hubble looked at the light from distant galaxies through the great 100-inch Hooker telescope at Mount Wilson, he found something that made the hair stand up on the back of every neck in astronomy. Every single galaxy he measured was redshifted. Every single one was moving away from us. But that was only the first half of the discovery. The second half was even more astonishing. Hubble noticed a pattern in the data, a relationship between how far away a galaxy was and how fast it appeared to be receding. The further away a galaxy was, the faster it was moving away from us. Not slightly faster, proportionally faster. A galaxy twice as far away was receding roughly twice as fast. A galaxy 10 times as far away was receding roughly 10 times as fast. This relationship, now known as Hubble's law, contained within it a single, inescapable, world-altering conclusion. The universe was not static. It was not permanent. It was not the same as it had always been. It was expanding in every direction, at every scale, all at once. Think about what that means for a moment. If the universe is expanding now, and if you run the clock backward in your mind, the universe must have been smaller in the past. Run it back far enough, and everything converges. All the galaxies, all the stars, all the matter and energy in the entire observable cosmos, compressed down into an unimaginably small, unimaginably hot, unimaginably dense point. The expansion of the universe, observed in the quiet data of a mountaintop telescope in California in 1929, was pointing directly at the beginning of time itself. Hubble did not set out to find the origin of the universe. He set out to measure the distances to galaxies, but the numbers told a story he could not have anticipated, and that story led all the way back to a moment before which the word before may not even have meaning. Einstein visited Hubble at Mount Wilson shortly after the data was published. He looked at the observations, he reviewed the measurements, and then, in one of the most gracious admissions in the history of science, he withdrew his cosmological constant. The correction he had inserted into his equations to prevent them from predicting an expanding universe was no longer needed. The universe was expanding, just as the unmodified equations had always predicted. Einstein later called his introduction of the cosmological constant the greatest mistake of his career. He had been so committed to the idea of a static, eternal cosmos that he had altered his own theory to fit a belief rather than letting the theory tell him the truth. It is a very human thing to do, and it is worth remembering that even the greatest minds in history sometimes resist the universe when it tries to tell them something they are not ready to hear. Hubble himself was a complicated figure. He was brilliant and ambitious, and by many accounts not particularly easy to work with. He had trained as a lawyer before turning to astronomy, and there was something lawyerly about the precision with which he built his case for an expanding universe. He did not speculate wildly. He gathered data, refined his measurements, checked and rechecked his calculations, and then let the numbers speak. The numbers spoke loudly. They said that the universe has a direction, that it is going somewhere, that it is not the same today as it was yesterday, or 1,000,000 years ago, or 1,000,000,000 years ago. That time has a shape, and that shape points outward, towards something larger, something cooler, something more diffuse than what came before. It is worth sitting with the weight of what was discovered that year on that mountain. For all of human history, in every culture and civilization and religious tradition on Earth, the sky had been understood as a fixed backdrop. The stars were eternal. The heavens were permanent. The cosmos was the one thing you could count on to remain exactly as it was. And then one man with a telescope and a spectrograph and a very careful eye for data looked up and discovered that the sky is not a backdrop at all. It is a surface in motion. It has been moving since the very first instant of existence. It will keep moving long after every civilization on this planet has risen and fallen and been forgotten entirely. The universe, Edwin Hubble showed us, is not a noun. It is a verb. It is not a thing that is. It is a thing that is becoming. And that single shift in understanding, from a cosmos that exists to a cosmos that expands, is perhaps the most profound revolution in the history of human thought. I want you to imagine a loaf of bread. Not a baked loaf, but an unbaked one, the kind that has just been shaped and is sitting in a warm oven beginning to rise. Inside the dough there are raisins, dozens of them, scattered throughout the raw loaf at various distances from each other. Now imagine the dough begins to expand slowly at first, then steadily, the way bread dough does when the yeast is working and the heat is right. As the dough grows, what happens to the raisins? They move apart. Every raisin moves away from every other raisin, not because any raisin is moving through the dough under its own power, but because the dough itself, the medium they are embedded in, is expanding. And here is the key detail. A raisin that was close to another raisin moves away from it slowly, but a raisin that was far away moves away much faster, because there is more expanding dough between them. The further apart two raisins are, the faster they separate. No raisin is at the center. Every raisin, from its own perspective, sees every other raisin moving away. This is the universe. This is not a loose analogy. It is the closest thing to an accurate picture of cosmic expansion that human language can construct without dissolving into pure mathematics. The galaxies are the raisins. The fabric of space itself is the dough, and the expansion is not something happening in space, it is something happening to space. The medium itself is growing, carrying everything embedded within it further apart with every passing second. There is no center to this expansion, no point from which everything is flying outward like shrapnel from an explosion. If you were standing in any galaxy, anywhere in the observable universe, you would see exactly what we see from Earth. Every other galaxy receding, the further ones receding faster, the whole cosmic landscape drawing away in every direction simultaneously. The universe is not exploding outward from somewhere. It is expanding everywhere, all at once, in the same way at every point. Now let us put some numbers on this, because numbers are where the raisin bread analogy stops being comfortable and starts being something else entirely. The Andromeda Galaxy, our nearest large neighbour, is about 2.5 million light-years away. That is 2.5 million years of light travel distance, which is already a number beyond ordinary intuition. But Andromeda is actually one of the rare exceptions, a galaxy close enough that the gravitational attraction between it and the Milky Way is strong enough to overcome the expansion. Andromeda is actually moving toward us, not away. In about 4.5 billion years, the two galaxies will merge. But beyond our immediate cosmic neighbourhood, beyond the small cluster of galaxies we are gravitationally bound to, every single galaxy is receding, and they are receding fast. The Virgo cluster, a massive collection of over 1,300 galaxies, roughly 54 million light-years away, is receding from us at approximately 1,200 kilometers per second. That is more than 4 million kilometers per hour. 4 million. The speed at which that cluster is moving away from us right now, as you breathe, as you blink, is fast enough to circle the Earth 100 times in a single hour. And yet on the cosmic scale, the Virgo cluster is practically a neighbour. Galaxies at the edge of the observable universe, billions of light-years away, are receding at speeds that approach, and in some cases exceed the speed of light. Not because they are moving through space that fast, but because there is so much space between us, and that space is expanding so rapidly that the cumulative recession velocity becomes astronomical. There are galaxies we can see right now, whose light is just barely reaching us, but which are already so far away that they will never be reachable. They are, in any practical sense, already gone. Here is the thing most people do not realize about this picture. The expansion does not affect everything equally. On very small scales, the universe is not expanding at all. Your body is not expanding. The Earth is not expanding. The solar system is not expanding. Even the Milky Way is not expanding. Gravity, electromagnetism, and the other fundamental forces that hold matter together are far stronger than the expansion of space at those scales. The expansion only becomes dominant over the vast gulfs between galaxy clusters, where gravity has no meaningful grip, and the stretching of space has nothing to compete with. Think of it this way. The expansion is like a very gentle current in an ocean. On small scales, it is completely overwhelmed by the local forces at work. A fish swimming in that current barely feels it. But over thousands of miles, the current adds up, and things that are far enough apart are carried in opposite directions without any force actively pushing them. The universe is that ocean, and the distances between galaxy clusters are those thousands of miles. What does it actually feel like to try to hold this in your mind? I find it does something unusual to my sense of scale. When you truly absorb the fact that everything beyond our local group of galaxies is receding, that the cosmos is emptying outward in every direction, that the distances between things are growing larger with every heartbeat, the universe stops feeling like a place and starts feeling like a process. It is not a container holding things, it is an event unfolding over time, and that shift from universe as place to universe as process is one of the most disorienting and somehow also one of the most peaceful reframings I know. Because a place can feel crowded or empty, near or far, owned or lost. But a process just unfolds. It does not ask for your permission. It does not wait for you to understand it. It simply continues at its own pace, in its own direction, carrying you with it whether you notice or not. And you are being carried right now. The galaxy you live in is embedded in the fabric of an expanding universe just like every other galaxy. The Milky Way is moving through space for its own gravitational reasons, but the space it inhabits is expanding around it, just as it expands around everything else. You are a raisin in the dough, a fixed point in a medium that is not fixed, and the raisins you can see from where you are, the galaxies visible through even the most powerful telescopes, represent only a fraction of what exists. Beyond the observable horizon, beyond the sphere of space from which light has had time to reach us in the universe's 13.8 billion year lifetime, there is almost certainly more, much more, possibly infinite more, an unobservable universe that dwarfs even the vast cosmos we can see, all of it expanding, all of it receding from all of it, endlessly, in every direction, with no edge and no center, and no sign of slowing down. Every single galaxy running away from every single other galaxy. Trillions of stars in each one, hundreds of billions of galaxies in the observable universe alone, all of them receding, all of them carried by the same expansion, all of them embedded in a fabric of space that has been growing since the first instant of existence and will not stop growing until the last light in the cosmos finally goes out. That is the universe you live in tonight, and somehow, in the middle of all that immensity and motion, you are here, still, quiet, breathing, wondering. It seems like exactly the right response. If the universe is expanding, and if you run that expansion backward in your mind like a film played in reverse, something remarkable happens. The galaxies stop receding and start approaching. The distances between things shrink. The vast cosmic web of clusters and filaments and voids compresses inward, growing denser and hotter as it contracts. Go back far enough and the galaxies themselves dissolve, their stars merging into a single undifferentiated sea of plasma. Go back further and even the atoms come apart, electrons stripped from nuclei by the ferocious heat, a universe of pure charged particles and radiation with no structure at all. And then, at the very limit of what our physics can describe, roughly 13.8 billion years ago, everything that exists was compressed into a state so small, so hot, so dense, that the words we use to describe physical things begin to lose their meaning entirely. This is where the story of the universe begins, not with a place, not with an object, but with a moment. We call it the Big Bang, which is one of the most misleading names in the history of science. It was not big in the sense that we normally use the word. It was, in its first instant, incomprehensibly small, smaller than an atom, smaller than a proton, smaller than anything you have ever tried to visualize. And it was not a bang, in the sense of an explosion happening inside some larger space. There was no larger space. Space itself did not exist before this moment, at least not in any form we can describe or model. The Big Bang was not an explosion in space. It was an explosion of space. The fabric of the universe, the medium in which everything exists, came into being in that first instant and has been expanding ever since. There was no before, there was no outside. There was only the beginning, and then the expansion, and then everything that followed. In the first fractions of a second, the universe was unimaginably hot. We're talking about temperatures of 10 million trillion degrees, numbers so large they dissolve into abstraction almost immediately. At those temperatures, none of the forces and particles we are familiar with existed in their current form. There was something called a quark-gluon plasma, a seething, undifferentiated soup of the most fundamental building blocks of matter, compressed together so tightly that the concept of individual particles barely applied. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single force at these temperatures, indistinguishable from one another, before separating out as the universe cooled and expanded. The first microseconds of the universe's existence were a physics experiment running at energies we will never be able to replicate, governed by conditions we can only model mathematically, in a space that was simultaneously everything and smaller than anything. Then the universe expanded, and as it expanded, it cooled. This is the fundamental relationship at the heart of cosmic history. Expansion means cooling. As space stretches, the energy within it spreads out, the temperature drops, and new structures become possible. Within the first 3 minutes, the universe had cooled enough for protons and neutrons to stick together, forming the nuclei of the lightest elements. Hydrogen, the simplest of all atoms, was the most abundant result. Helium came next, tiny traces of lithium, that is it. Those 3 elements, produced in the fire of the Big Bang's first few minutes, are the raw material from which everything in the universe has been built. The carbon in your body, the oxygen in your lungs, the iron in your blood, all of it came later, forged inside stars that would not exist for hundreds of millions of years. But the hydrogen that fuels those stars, the hydrogen that makes up most of the observable universe, was born in those first 3 minutes of cosmic fire. For the next roughly 380,000 years, the universe was opaque. Light existed, but it could not travel freely. The universe was so dense and hot that photons, particles of light, were constantly scattering off the charged particles around them, unable to move in a straight line for more than a tiny distance before being deflected again. The universe was a fog, a bright, hot, uniform fog of plasma and radiation with no transparency and no structure. Nothing could see through it, because there was nothing to see and no way for light to carry information across any meaningful distance. Then, 380,000 years in, the universe cooled enough for electrons to combine with nuclei and form neutral atoms for the first time. The fog lifted, light was suddenly free to travel, and the universe became transparent in a moment that astronomers call recombination, or sometimes the epoch of last scattering. The light released in that moment, the first light to ever travel freely through the universe, is still traveling today. We can detect it. It fills the entire sky, coming equally from every direction, a faint whisper of microwave radiation with a temperature of just under 3 degrees above absolute zero. We call it the cosmic microwave background, and it is the oldest light in the universe, a direct image of what the cosmos looked like 380,000 years after the Big Bang. When you see those famous oval maps of the early universe, covered in faint blotches of slightly warmer and slightly cooler regions, you are looking at a baby photograph of everything that exists. Those tiny temperature variations, ripples in the primordial fog, were the seeds of all the structure that would follow. The slight overdensities in that early plasma would eventually, over hundreds of millions of years, collapse under gravity to form the first stars, the first galaxies, and ultimately the web of cosmic structure we observe today. There is something almost impossible to sit with in all of this. The fact that the universe had a beginning, a genuine, actual first moment, before which there was nothing, and after which there was everything. Every human culture that has ever existed has had a creation story, some narrative to explain why there is something rather than nothing. But the scientific picture is, in its own way, more astonishing than any of them, because it is not a story about a god shaping matter out of chaos, or a cosmic egg cracking open to release the world. It is a story about space itself coming into being, about time beginning at the same moment as matter and energy, about the entire universe emerging from a state so extreme that our physics loses its grip trying to describe it. We do not know what caused the Big Bang. We do not know if the word caused even applies to a moment that may have preceded causality itself. These are open questions, genuinely open, the kind that physicists and philosophers are still wrestling with and may wrestle with for a very long time. But here is what we do know. Whatever that first moment was, it contained within it the seeds of everything you have ever seen, touched, thought, or loved. The expansion that began then is the same expansion still running tonight, carrying the galaxies apart, stretching the fabric of space in every direction, driving the universe toward whatever it is becoming. You're a product of that expansion. Your atoms were forged in the interiors of stars that formed because of the density fluctuation seeded in those first 380,000 years. The ground beneath you, the air around you, the thoughts moving through your mind right now, all of it traces back to that single, irreducible, mysterious first moment. The universe began, and in beginning, it made you possible. Hold that thought gently as we continue. The year was 1998. Two teams of astronomers, working independently, in quiet competition with each other, were trying to answer what seemed like a straightforward question. They already knew the universe was expanding. Hubble had established that nearly 70 years earlier. What they wanted to know was how fast that expansion was slowing down. Because of course it was slowing down. Everything in the universe pulls on everything else through gravity, and gravity is a brake. The Big Bang had sent everything flying outward, but the collective gravitational attraction of all that matter should have been tugging it back, decelerating the expansion over billions of years. The question was simply, how much? Was there enough matter to eventually halt the expansion entirely and cause the universe to collapse back in on itself? Or would the expansion continue forever, just gradually losing momentum like a ball thrown upward that never quite falls back? These were the two scenarios on the table, and both teams were confident they would find evidence for one of them. They found neither. What they found instead was something so unexpected, so thoroughly outside the range of what anyone had predicted, that the lead researchers spent weeks checking and rechecking their data before they were willing to say it out loud. The universe was not decelerating. It was not slowing down at all. It was speeding up. The expansion of the universe, rather than losing momentum under the influence of gravity, was accelerating. The galaxies were not just moving apart. They were moving apart faster today than they were 1 billion years ago, faster than they were 5 billion years ago. Something was pushing the expansion forward, overcoming the gravitational pull of all the matter in the observable universe and driving the cosmic fabric apart at an ever-increasing rate. No one had predicted this. No existing theory had required it. It arrived in the data like a message from a universe that had been keeping a very significant secret. The two teams involved in this discovery were led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other. They were using a particular type of exploding star called a Type Ia supernova as a cosmic measuring tool. Here is why that works. When a certain kind of white dwarf star reaches a critical mass and explodes, the explosion always releases roughly the same amount of energy. Always. The physics of the detonation is so consistent that astronomers can use these supernovae as what they call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. The dimmer it looks, the further away it must be. By measuring the brightness of Type Ia supernovae in distant galaxies and comparing those measurements to the galaxy's redshifts, both teams could map the history of the universe's expansion in precise detail, and that map showed an acceleration no one was prepared for. The implications were immediate and staggering. If the universe is accelerating, there must be something causing that acceleration. Some form of energy or force that acts in opposition to gravity, pushing space apart rather than pulling things together. Physicists needed a name for it, and they reached back to something familiar. Einstein's discarded cosmological constant. The mathematical fudge he had introduced to keep his equations predicting a static universe, and then abandoned when Hubble showed the universe was expanding, turned out to describe exactly the kind of energy needed to explain the acceleration. The constant Einstein had called his greatest mistake was, it appeared, not a mistake at all. It was a prediction. A prediction of something real, something embedded in the structure of space itself, causing the fabric of the universe to push outward from within. They named it dark energy, and it changed everything. Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. The Nobel Committee described it as one of the most surprising findings in modern cosmology. That is an understatement of considerable proportion. It was not just surprising, it was reality restructuring. Because once you accept that the universe's expansion is accelerating, you are forced to accept everything that follows from it. The future of the cosmos is not a gentle coasting to a stop, or a slow gravitational collapse back to a single point. It is an endless, ever faster expansion into a cold and empty dark. Structures that exist now, galaxies, clusters, the webs of cosmic filaments that give the universe its large-scale architecture will be progressively pulled apart, isolated, scattered across distances so vast that the concept of connection between them becomes meaningless. The universe is not just expanding, it is running away from itself. Here is the thing most people do not realize about the 1998 discovery. It did not just tell us something new about the future, it told us something new about what the universe is made of. Before the discovery of acceleration, the cosmic inventory looked roughly like this: ordinary matter, the atoms and molecules and particles that make up everything you can see and touch and measure, accounted for a few % of the total energy content of the universe. Dark matter, a form of matter that interacts gravitationally but does not emit or absorb light, accounted for roughly 27%. Together, they made up the full 100% of what physicists thought the universe contained. Then the acceleration data arrived and rewrote the balance sheet entirely. To drive the observed acceleration, approximately 68% of the universe's total energy content must consist of dark energy. 68%. More than 2/3 of everything that exists is made of something we have no direct evidence for, no detector capable of measuring, and no fundamental theory that fully explains. Let that sink in for a moment. The universe, in its totality, is about 5% ordinary matter. Everything you have ever seen, every star, every planet, every galaxy, every cloud of gas and dust, every atom that has ever been part of anything, accounts for just 5%. The remaining 95% is dark matter, roughly 27%, which we infer from its gravitational effects but cannot directly observe, and dark energy 68%, which we infer from the acceleration of the expansion, but cannot directly detect, measure, touch, or explain. We live in a universe in which the vast majority of what exists is invisible to us, unknown to us, and in the case of dark energy, made of something that does not even behave like ordinary matter or energy in any way we can currently model. The universe is almost entirely mystery. We are the 5% trying to understand the 95%. And yet, for all its strangeness, the discovery of 1998 was made with patient, careful, methodical science. Two teams of researchers, in quiet competition, using exploding stars as measuring tools, finding a result neither expected and both initially doubted, checking it against every possible source of error, and then having the scientific integrity to report what the data actually said rather than what they had hoped it would say. There is something deeply moving about that. The universe handed humanity one of the most disorienting facts in the history of knowledge, and two groups of astronomers received it with honesty, rigor, and eventually a Nobel Prize. The universe accelerates, we don't know why, and somehow sitting with that not knowing in the dark, in the quiet of a late night when the world is still and the questions feel largest, is one of the most alive feelings I know. There is something out there that makes up more than 2/3 of everything that exists. It has no colour, no texture, no temperature. It does not emit light, absorb light, or interact with light in any way we can measure. It has no known particle associated with it. No detector on Earth has ever registered its direct presence. It cannot be bottled, isolated, or studied in a laboratory. It passes through matter without leaving any trace, and yet it is everywhere, distributed with extraordinary uniformity throughout the fabric of space itself, present in every cubic centimetre of the universe, in the void between galaxies and in the space between your fingers, and in the vast empty reaches between galaxy clusters that contain, as far as we can tell, absolutely nothing else. It is the dominant component of the cosmos. It shapes the ultimate fate of everything, and we have given it a name that is really just an admission of ignorance. We call it dark energy. Dark because we cannot see it, energy because it does something, and the gap between those two words contains most of what we do not understand about the universe. Let me try to give you a sense of what dark energy actually does, even if we cannot say what it is. Ordinary energy and matter, everything you have ever encountered, behaves in a consistent way inside an expanding universe. As space expands, the density of matter decreases. Think of the same number of particles spread across a larger and larger volume. They thin out, their collective gravitational influence weakens, and radiation, like light, loses energy as the universe expands, its wavelength stretching along with space itself, growing redder and cooler. Everything dilutes, everything weakens. This is why the expansion of the universe was expected to decelerate. As matter thinned out, its gravitational braking effect should have gradually overcome the initial momentum of the Big Bang. Dark energy does not behave this way. As space expands, the density of dark energy stays constant. It does not dilute. It does not thin out. Every new cubic centimetre of space that comes into existence through expansion contains the same amount of dark energy as every cubic centimetre that existed before. The more the universe expands, the more dark energy it contains in total. And the more dark energy it contains, the faster it expands. The acceleration feeds itself. It is a runaway process, and it has been running for billions of years. This property, constant energy density in an expanding space, is so strange that it has no good analogy in ordinary experience. Everything else we know about energy follows rules that make intuitive sense. Heat spreads out and dissipates. Light dims with distance. Sound fades. Even the gravitational pull of a massive object weakens as you move away from it, following the inverse square law that Newton described 3.5 centuries ago. Dark energy follows none of these rules. It is intrinsic to space itself, not to the matter or radiation within it. When space grows, dark energy grows with it. As if the vacuum of space has a built-in energetic pressure that never weakens, never fades, never runs out. It is not a force applied from outside. It is a property of the medium itself. Space, in other words, is not empty. Space has energy. And that energy is tearing the universe apart. The most mathematically precise description of dark energy we currently have is Einstein's cosmological constant, the same term he introduced and then withdrew from his equations of general relativity. When interpreted in the context of modern quantum physics, the cosmological constant represents the energy density of the vacuum, the baseline energy that empty space possesses simply by virtue of existing. Quantum mechanics tells us that empty space is not truly empty. It seethes with what physicists call vacuum fluctuations, virtual particles constantly popping in and out of existence, borrowing energy from the vacuum for tiny fractions of a second before annihilating each other and returning that energy. This quantum activity gives the vacuum an intrinsic energy, a measurable pressure. And when you calculate how much vacuum energy quantum mechanics predicts, you get a number, a very specific number. The problem, and it is one of the most embarrassing problems in all of theoretical physics, is that the number quantum mechanics predicts for the vacuum energy is roughly 10 to the power of 120 times larger than the value of the cosmological constant we actually observe. That is a 1 followed by 120 zeros. The prediction and the observation disagree by a factor so incomprehensibly large that physicists have given this discrepancy its own name, the cosmological constant problem. It is the worst prediction in the history of science. Something is cancelling almost all of that predicted vacuum energy, leaving only a tiny, tiny residue, the value we observe as dark energy. But we have no idea what is doing the cancelling, or why the residual value is what it is, or whether it is truly constant over time or slowly changing. Some physicists have proposed that dark energy is not a fixed property of space, but a dynamic field that evolves as the universe ages, something they call quintessence. If dark energy is changing over time, even very slowly, the implications for the ultimate fate of the universe are dramatically different from the simple cosmological constant picture. A growing dark energy could eventually overcome even the forces holding atoms together, leading to an end called the Big Rip. A weakening dark energy could allow gravity to eventually reassert itself, slowing the expansion and perhaps reversing it. We do not know which scenario is correct because we do not know what dark energy is. We have its fingerprints, we do not have its face. Here is the thing most people do not realize about this situation. It is not a gap in our knowledge waiting to be filled by the next generation of telescopes. It is a fundamental conceptual challenge. The two great pillars of modern physics, general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles and forces at the smaller scales, are both extraordinarily successful theories. Each one makes predictions that have been tested to extraordinary precision, and yet they are fundamentally incompatible with each other. They cannot both be completely right, because when you try to apply them simultaneously to the same problem, as you must do when thinking about dark energy, they produce answers that contradict each other by a factor of 10 to the power of 120. Dark energy is not just a mystery about what is in the universe. It is a symptom of an unresolved fracture at the heart of our understanding of how reality works. And yet, for all its inscrutability, dark energy is doing something measurable, something observable, something that leaves its signature in the structure of the cosmos for anyone with the right instruments and the patience to read it. We see it in the acceleration of distant supernovae. We see it in the distribution of galaxies across billions of light years. We see it in the subtle patterns of the cosmic microwave background, the ancient light left over from the early universe. Dark energy is not a hypothesis or a speculation, it is a measured reality. Something is out there, in the fabric of space itself, pushing the universe apart with a steady, patient, inexorable force that has been operating since the universe was roughly 5 billion years old and shows no sign of relenting. We have named it, we have measured it, we have written equations that describe its effects with remarkable precision. We just have absolutely no idea what it actually is. And somehow, in the small hours of a quiet night, I find that more fascinating than terrifying. The universe is keeping its deepest secret, and we are the creatures trying, with patient persistence, to ask it the right questions. Close your eyes for a moment and imagine perfect emptiness. A region of space with nothing in it. No stars, no planets, no dust, no gas, no radiation, no particles of any kind. Just pure, absolute vacuum. A void so complete that if you were somehow placed inside it, you would have no sensory input whatsoever. No light to see by, no air to breathe, no surface to touch, no sound to hear, just darkness and silence and nothing. Most people, when they imagine the vacuum of space, imagine something like this: a passive, inert, featureless nothingness that serves as the backdrop against which the real action of the universe takes place, a container, an absence, the space between things that has no properties of its own. This intuition is natural. It is also completely wrong. Empty space is not empty. It has never been empty. And understanding what it actually is, what it contains, what it does, and why that matters, takes you directly to the heart of the deepest unsolved problem in physics. Quantum mechanics, the branch of physics that describes the behavior of the universe at its smallest scales, makes a very specific and very strange claim about the vacuum. It says that empty space is not a passive background, but an active, seething, energetic medium. At any given point in the vacuum, at any instant in time, pairs of particles are spontaneously appearing from nothing, existing for an inconceivably brief moment, and then annihilating each other and vanishing back into nothing. These are called virtual particles, and they are not a metaphor or a theoretical convenience. They have measurable effects. The Casimir effect, first predicted in 1948 and experimentally confirmed many times since, demonstrates that two uncharged metal plates placed very close together in a vacuum experience a tiny but real attractive force. The reason is that the virtual particle activity in the space between the plates is slightly suppressed compared to the activity outside them, creating a pressure difference that pushes the plates together. The vacuum is pushing, the nothing is doing something, and that means the nothing is not nothing at all. This constant quantum activity in the vacuum is called vacuum fluctuation, or sometimes zero-point energy. The zero point refers to the fact that even at absolute zero temperature, the lowest temperature theoretically possible, when all thermal motion has ceased and every system is in its lowest possible energy state, the vacuum still fluctuates. It cannot stop. Quantum mechanics, specifically the Heisenberg uncertainty principle, forbids it. The uncertainty principle says that the more precisely you know the energy of a system at a specific moment in time, the less precisely you can know the time itself, and vice versa. Perfect stillness, a vacuum with exactly zero energy at every moment, would require perfect knowledge of both energy and time simultaneously. Quantum mechanics does not allow this. The vacuum must fluctuate. It is written into the mathematical structure of reality at the deepest level we can currently probe. Emptiness is forbidden by the laws of physics. Now here is where this connects to dark energy, and where it becomes both beautiful and deeply troubling. If the vacuum has energy, and quantum mechanics is absolutely clear that it does, then that energy has gravitational effects. Einstein's general relativity tells us that energy and mass are equivalent, that anything with energy warps the fabric of space-time around it. Vacuum energy, spread uniformly throughout all of space, would therefore exert a kind of pressure on the universe itself, a cosmological pressure. And crucially, the kind of pressure that vacuum energy exerts is not the ordinary outward pressure of a gas pushing against its container. It is a negative pressure, a tension, a pull on space that counterintuitively causes the expansion of the universe to accelerate rather than decelerate. Vacuum energy, if it exists, does exactly what dark energy does. It pushes the universe apart from the inside. Many physicists believe that dark energy simply is vacuum energy, that the cosmological constant Einstein introduced and then withdrew is not a mathematical trick but a real physical property of space, the energy density of the quantum vacuum expressed at cosmic scales. But then we arrive at the problem mentioned in our previous chapter, and it deserves to be dwelt on because it is genuinely one of the most extraordinary failures of prediction in the history of science. When physicists use quantum field theory, the mathematical framework that describes the quantum vacuum, to calculate how much energy the vacuum should contain, they get an answer, a very precise answer. And when they compare that answer to the value of the cosmological constant that we actually observe from measurements of the universe's expansion, the two numbers disagree by a factor of 10 to the power of 120. To give you a sense of that discrepancy, there are estimated to be roughly 10 to the power of 80 atoms in the entire observable universe. The disagreement between the predicted and observed vacuum energy is incomparably larger than the number of atoms in everything we can see. It is the largest discrepancy between a theoretical prediction and an experimental observation that has ever been recorded in any field of science. something is cancelling almost all of the vacuum energy, leaving only an almost imperceptibly tiny residue. And we have no idea what is doing the cancelling. This problem has a name. Physicists call it the cosmological constant problem, and it sits at the intersection of quantum mechanics and general relativity like a stone wall marking the boundary of current human understanding. Some proposed solutions invoke the idea of supersymmetry, a theoretical framework that postulates a partner particle for every known particle, which would cause most of the vacuum energy contributions to cancel each other out. Others invoke the multiverse, a landscape of an almost incomprehensible number of possible universes, each with a different value of the cosmological constant, and argue that we necessarily find ourselves in one with a very small value, because only universes with small cosmological constants allow structures like galaxies and stars and planets and life to form. This is called the anthropic argument, and it makes many physicists deeply uncomfortable, because it feels less like an explanation and more like an acknowledgement that we may never have a deeper one. What strikes me most about all of this is not the size of the problem but its location. The mystery of dark energy is not hiding somewhere distant and inaccessible. It is here. It is in the space between your hands right now. It is in the air in front of your face. It is in every cubic centimetre of the room around you. The vacuum of space is not something you need a rocket ship to reach. It is right here, threaded through the matter of everyday life, humming with quantum activity, brimming with an energy we can measure but not explain. The universe's deepest secret is not locked away at some cosmic frontier. It is everywhere, all at once, present in the most ordinary emptiness imaginable. There is a kind of quiet vertigo in that realization. The space between things, the gaps and silences and pauses that we normally treat as absences, turns out to be the dominant ingredient of the universe. The emptiness is not background, it is substance. The void is not nothing. It is the most abundant something we know of, and it is expanding, carrying everything with it, driven by an energy we have named but not understood, written into the structure of reality at a level beneath anything our instruments can yet reach. You are surrounded by it. You are immersed in it. You have been swimming in the vacuum's quantum hum your entire life without knowing it. And somewhere in that hum, if we can only learn to listen correctly, is the answer to why the universe is the way it is. We are still learning how to listen. You have probably heard that nothing can travel faster than the speed of light. It is one of the most famous facts in all of science, the ultimate cosmic speed limit, established by Einstein's special theory of relativity and confirmed by more than a century of experimental evidence. Light travels at approximately 186,000 miles per second. Nothing with mass can reach that speed. Nothing can exceed it. This rule is absolute, and as far as we can tell, it applies everywhere in the universe without exception. But here is something that most people are never told, something that sits quietly at the edge of that famous rule and changes everything about what it means. The speed of light is a limit on how fast things can move through space. It says nothing about how fast space itself can move, and space, it turns out, has no speed limit at all. This distinction is subtle, but its consequences are enormous. When two galaxies are far enough apart, the expansion of space between them can cause the distance separating them to grow faster than light could ever travel. Not because either galaxy is moving through space at superluminal speed, neither one is violating Einstein's limit. Each one, in its own local region of space, is moving at perfectly ordinary speeds. But the space between them is expanding, and if there is enough of it, the cumulative growth can add up to a recession velocity that exceeds the speed of light. This is not science fiction. It is happening right now in the observable universe with galaxies we can actually see. There is a boundary, a spherical surface surrounding us in every direction, beyond which galaxies are receding from us faster than light. That boundary is called the Hubble horizon, or sometimes the cosmic event horizon, and everything beyond it is, in a very precise and permanent sense, beyond our reach forever. Let me give you a sense of where that horizon lies. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of roughly 46 billion light years. You might expect the Hubble horizon to coincide with the edge of the observable universe, but it does not. The Hubble horizon, the distance at which recession velocities equal the speed of light, is currently about 14 billion light years away. This means that a significant portion of the galaxies we can currently observe are already beyond the Hubble horizon. Their light reached us in the past, when they were closer, when the expansion had not yet carried them past the threshold. But any signal we sent to them today would never arrive. The space between us and them is growing faster than any signal could cross it. We can see them. We can study the ancient light they emitted billions of years ago, but we can never contact them, never reach them, and never receive any new information from them. They are visible, but permanently inaccessible. A library you can see through a window but never enter. And the horizon is not static. It is moving. As the expansion of the universe accelerates, driven by dark energy, the Hubble horizon is effectively shrinking in terms of the number of galaxies it encompasses. Galaxies that are currently just inside the threshold, whose recession velocities are just below the speed of light, will eventually be pushed across it by the ongoing acceleration. They will cross from the reachable to the unreachable, from the communicable to the forever silent. And once a galaxy crosses that horizon, it does not simply become very far away. It becomes cosmologically severed. The light it emits after crossing the horizon will never reach us, no matter how long we wait. It is gone in the most absolute sense that word can carry in a physical description of reality. Here is the thing most people do not realize about this process. It means the observable universe is shrinking in terms of content, even as it grows in terms of physical size. The universe is getting larger, but the portion of it we can ever know anything about is getting smaller. Information is being permanently lost, not through any violent process, not through any destruction of matter or energy, but simply through the relentless expansion of the space between things. The universe is forgetting itself. Each crossing of the cosmic horizon is a small, quiet, permanent erasure. A galaxy that took billions of years to form, that contains hundreds of billions of stars, that may harbour planets and perhaps life and perhaps minds that look up at their own sky and wonder about the cosmos, slips silently beyond our reach, and we have no way of knowing it has gone. No alarm sounds, no signal arrives to announce the departure. One moment its ancient light is reaching us. The next, in cosmic terms, it is not. There is a thought experiment I find both beautiful and quietly devastating. Imagine a civilization somewhere in a distant galaxy, billions of light years from here, looking out at the universe as it exists in their own time. If they have developed the equivalent of our telescopes and our cosmology, they would observe the same basic picture we observe, a vast cosmos of galaxies, all receding, the expansion accelerating, a Hubble horizon beyond which they cannot reach. They would wonder about the scale of the universe, about what lies beyond what they can see, about the nature of the force driving the expansion. Their universe would look very much like ours, but their observable universe would be centered on them, not on us. The galaxies they can see and the galaxies we can see would overlap only partially. There are regions of the universe that no civilization anywhere will ever be able to observe, because the light from those regions has never had time to reach anyone and the expansion is ensuring it never will. The universe contains information that will never be known, questions that will never have answers, not because the answers do not exist, but because the universe is physically structured in a way that prevents them from ever being received. This is what the cosmic speed limit, the real one, the one that applies to space itself rather than to things moving through it, actually means when you follow it to its conclusion. It means the universe is inherently, irreversibly, and increasingly divided, not by walls or barriers in the ordinary sense, but by the geometry of expanding space and the finite speed of information. The cosmos is larger than the observable is larger than the reachable is larger than what we will ever actually reach. And at every level the gap is growing. The universe is not just big, it is structured in a way that ensures most of it will always remain unknown, even in principle, even given unlimited time and technology and curiosity. That is not a limitation of our instruments. It is a feature of the universe itself written into its expansion, sealed by the speed of light, growing larger with every second that dark energy drives the acceleration forward. I find something strangely peaceful in this, even though it is also genuinely terrifying. There is a completeness to it. The universe is vast beyond comprehension, and most of it is forever beyond reach. And somehow, That makes the portion we do inhabit feel more precious rather than less. We're inside the horizon. We're in the reachable, knowable, observable slice of a cosmos that extends unimaginably further in every direction. And in this slice, right now, tonight, the stars are still visible and the questions are still open, and the light from ancient galaxies is still arriving at our eyes. The horizon has not closed around us yet. We still have the whole sky. We still have tonight. Right now, as you lie in the dark, as the room around you sits in perfect stillness, and the world outside your window holds its quiet, nighttime breath, galaxies are vanishing. Not exploding, not colliding, not burning out, simply vanishing in the most permanent and irreversible way the universe permits, by crossing the cosmic horizon and passing beyond the reach of any signal, any light, any connection to the portion of the universe we inhabit. It is happening continuously, silently, at a rate of roughly 1 galaxy per year crossing beyond our cosmic event horizon forever. That number sounds almost manageable until you sit with what it means. Each of those galaxies contains hundreds of billions of stars. Each of those stars may have planets. Each of those planets exists in a universe undergoing processes and harboring possibilities we will never know about. And every year, one more of those entire worlds of possibility steps permanently off the edge of our knowable cosmos and does not come back. This is not a future concern. It is not something that will begin to happen in 1 billion years when the universe has aged considerably further. It is happening now. The galaxies currently crossing our cosmic event horizon are doing so because the universe has already been accelerating for roughly 5 billion years, long enough for dark energy to have pushed a significant fraction of the observable universe's contents past the point of no return. When astronomers map the large-scale structure of the cosmos and identify the most distant galaxy clusters at the edges of our observational reach, some of those clusters are already in the process of their final farewell. Their light is still arriving at our telescopes today, ancient light emitted when the universe was young and those galaxies were closer. But the relationship is already severing. The thread of light connecting them to us is already, in a sense, the last thread. A correspondence that has been running for billions of years is quietly coming to its end. Now project this forward in time, not billions of years, but trillions. Numbers so large they require a different relationship with the concept of duration than we normally use. In roughly 100 billion years, most of the galaxies currently visible in our night sky will have receded beyond our cosmic event horizon. The Milky Way and Andromeda will by then have merged into a single large elliptical galaxy, sometimes called Milkomeda by astronomers who enjoy giving things evocative names. That merged galaxy will be part of a small cluster of gravitationally bound neighbours, roughly a handful of galaxies all told, the remnant of what we currently call the local group. And beyond that cluster in every direction, the universe will appear empty. Not because there are no other galaxies, there will be hundreds of billions of them, but they will all be beyond the horizon, receding faster than light, invisible and unreachable and unknown. The night sky, for any civilization that might exist in that era, will be very nearly dark. A few thousand stars, one galaxy visible to the naked eye at most, and beyond that, nothing. Think about what that means for any hypothetical future astronomers living in that era. They would look out at their universe and see a single island of stars surrounded by emptiness. If they were scientifically sophisticated enough to develop the equivalent of our cosmology, they would have a profound problem. They would have no observational evidence that other galaxies exist at all. There would be no redshifted light from distant galaxies to measure, no Hubble flow to detect, no cosmic microwave background easily distinguishable from other sources of noise. They would have no way of knowing that the universe was expanding, because all the evidence for that expansion, the receding galaxies, the large-scale structure, the background radiation, would either be gone or so diluted as to be undetectable. They would look at their small isolated island of stars and conclude, reasonably but incorrectly, that this was the whole universe. The entire knowledge base that we have painstakingly assembled over the past century, the expanding universe, the Big Bang dark energy, would be not just unknown but unknowable to them. The universe will have erased the evidence of its own history. Here is the thing most people do not realize about this. We are the lucky ones. We exist at the one moment in cosmic history when the universe is still populated enough, and the expansion has proceeded far enough to be measurable, but not so far as to have erased the evidence that we can actually figure out what is going on. The cosmic microwave background is still detectable. The redshifts of distant galaxies are still measurable. The large-scale structure of the cosmos is still visible. The evidence is all around us, available to anyone with the patience to gather it and the mathematical tools to interpret it. A civilization born 1 trillion years from now, in the cold and empty universe of the deep future, will have none of this. They will be epistemically stranded, surrounded by an emptiness that gives no hint of its own origin or structure. We happen to have been born at exactly the right moment to see the universe as it truly is. That is an extraordinary piece of luck, if luck is even the right word for something that required 4 billion years of planetary evolution to produce a species capable of appreciating it. There is another layer to this disappearing act that I find particularly affecting. It is not just galaxies that are eventually lost to the expansion, it is light itself. As galaxies recede and their light becomes increasingly redshifted, the wavelengths of the photons they emit grow longer and longer, stretched by the expansion of space. Eventually the light becomes infrared, then microwave, then radio waves of such long wavelength that they become essentially undetectable. The galaxy does not suddenly go dark, it fades. Slowly, over billions of years, it grows dimmer and redder and cooler and quieter, until it crosses below any threshold of detectability and is gone not with a dramatic ending, but with a gradual, patient diminishment into silence. It is the most peaceful kind of disappearance imaginable. A slow dimming rather than an extinction. A drift into quiet rather than a plunge into dark. And there is, if you allow yourself to feel it, something almost tender about it. The universe saying farewell in the only language it knows, the language of fading light. We are watching the universe lose its memory in slow motion. Each galaxy that crosses the horizon takes with it a chapter of the cosmic story, a set of physical events and structures and processes that will never be known to us or to anyone on our side of the expanding void. The universe is larger than it will ever be knowable, and it is getting less knowable with every second, but tonight it is still knowable enough. The sky is still full of ancient light, the galaxies are still there, still broadcasting their long, travelling messages across the dark, still telling us their stories in the only way they can, by shining. Tonight they are still shining, and we are still here to receive them. There is something in that simple, temporary, precious fact that feels worth pausing for, worth breathing slowly around, worth holding gently in the mind as the night deepens and the stars continue their long, patient, quietly terminal broadcast. We have been talking about the expansion of the universe as though it is a fixed and constant thing, a steady stretching of space that has been proceeding at a measurable rate and will continue to do so indefinitely. And for the purposes of everything we have discussed so far, that picture is accurate enough. But here is a detail that physicists have not been able to rule out, a possibility that sits at the edge of our current understanding of dark energy and casts a very particular kind of shadow over the long-term future of everything that exists. What if dark energy is not constant? What if, rather than maintaining a fixed energy density as space expands, dark energy is actually growing stronger over time, not just keeping pace with the expansion, but accelerating it ever more aggressively, becoming more and more potent with every passing billion years, until it reaches a strength capable of overcoming not just the gravity between galaxies, but the forces holding galaxies together, then solar systems, then planets, then mountains, then molecules, then atoms themselves. What if the expansion does not just continue forever, but intensifies until it tears the fabric of everything apart? This scenario has a name. Physicists call it the Big Rip, and it is one of the most viscerally unsettling endings the universe could have. The Big Rip was first formally described in 2003 by physicist Robert Caldwell and his colleagues. It arises from a specific class of dark energy models in which the dark energy density does not remain constant, but increases over time. In the language of physics, this requires dark energy, with what is called a phantom energy equation of state, a relationship between its pressure and density that places it in territory even more exotic than the standard cosmological constant. If dark energy behaves this way, its repulsive effect grows progressively stronger as the universe ages. The expansion of the universe does not just accelerate smoothly and indefinitely, it accelerates at an accelerating rate. The growth of space becomes faster and faster and faster in a runaway process that eventually overwhelms every other force in nature, one by one, in order of their strength, until nothing that is held together by anything remains held together by anything. Let me walk you through how it would unfold slowly, because the sequence is both fascinating and deeply strange. In the scenario calculated by Caldwell's team, assuming a specific set of phantom energy parameters, the Big Rip would occur roughly 22 billion years from now. For most of that time, the universe would look broadly similar to how it looks today. Galaxies would continue to drift apart, stars would continue to burn, and from inside a stable solar system the cosmic expansion would be as invisible as it is tonight. Then, in the final billion years before the end, the expansion would begin to affect even gravitationally bound structures. Galaxy clusters would start to be pulled apart, their member galaxies drifting away from each other as the repulsive force of dark energy finally overcomes the gravitational bonds holding them in place. The universe would begin to look emptier, more isolated, more fragmented at the larger scales. In the final 100 million years, individual galaxies would be torn apart. The stars within them, which have been travelling together through space for billions of years, would be flung away from each other as dark energy overwhelms the gravitational glue of the galaxy itself. The Milky Way, or whatever it has become by then, would dissolve. Its stars would scatter into the expanding void, each one an isolated island of light in a universe that has stopped making structural sense. In the final months before the end, solar systems would be disrupted. The expansion would grow strong enough to overcome the gravity-binding planets to their stars. Earth, if it still existed in any recognizable form, would spiral away from the Sun. The familiar architecture of the solar system, the orbits, the gravitational dance that has been running for 4.5 billion years, would come apart. In the final minutes, planets and moons would be shredded. Mountains and oceans would be pulled into the expanding space. Matter itself would lose cohesion at larger and larger scales as the force driving the rip grows more powerful than the electromagnetic forces holding solid objects together. And then, in the final fraction of a second before the Big Rip, atoms themselves would be torn apart. The electrons orbiting atomic nuclei, held in place by electromagnetic attraction, would be ripped free. The nuclei, held together by the strong nuclear force, the most powerful force in nature, would be shredded. Protons and neutrons would dissolve, and at the very last instant space-time itself would be torn, the fabric of the universe ripped at the Planck scale, ending not with darkness or cold or stillness, but with a violence so total and so fundamental that nothing of any kind could survive or persist, or even be said to exist afterward. Complete annihilation. Not of individual things, but of the capacity for things to exist at all. The universe would end in the most absolute sense of that word that physics can describe. Here is the thing most people do not realize about the Big Rip. It is not the most likely scenario. Current measurements of dark energy suggest that its density is consistent with a cosmological constant, a fixed value that does not change over time. If that is correct, the Big Rip does not occur, and the universe instead faces the quieter and in some ways more melancholy fate of the Big Freeze, which we will come to shortly. But the data is not yet precise enough to definitively rule out a phantom energy equation of state. The measurements have error bars, uncertainties, ranges within which a slowly increasing dark energy could be hiding. Future surveys and telescopes, including the Euclid space mission launched in 2023 and designed specifically to measure the properties of dark energy with unprecedented precision, may eventually close those error bars enough to tell us whether the Big Rip is truly off the table or whether it remains a genuine cosmic possibility. What I find most striking about the Big Rip is not its violence but its intimacy. It does not end the universe from the outside, through some external catastrophe imposed on a passive cosmos. It ends it from the inside, through the intensification of a property that is already present in every cubic centimetre of space right now. The force that would eventually tear atoms apart is the same force that is currently, gently, imperceptibly, pushing distant galaxies apart. Dark energy is already here. It is already doing its work. The Big Rip, if it happens, would not be the arrival of something new. It would be the culmination of something that has been unfolding since the universe was 5 billion years old, growing imperceptibly stronger, approaching some threshold that either exists or does not, and that our current observations cannot yet definitively distinguish. There is a strange kind of vertigo in knowing that the same force acting on the universe tonight, the same expansion that is silently stretching the space between galaxies while you breathe and the room stays still, could in principle be the seed of the most violent ending imaginable, or could simply be the beginning of a long, slow, cold, quiet fade. We do not yet know which. We are living inside the process, unable to see its end from where we stand, watching the numbers refine themselves with each new generation of telescopes, waiting for the data to tell us which kind of forever the universe has chosen. Tonight, the answer is still open. Tonight, both endings are possible, and in a strange way that openness, that not yet knowing, is its own kind of gift. If the Big Rip is the universe ending in violence, the heat death is the universe ending in peace. In a peace so complete, so uniform, so total, that the word peace no longer quite captures it. It is not the peace of a sleeping world or a quiet night. It is the peace of absolute equilibrium, a state in which nothing changes because nothing can change, in which every gradient of temperature and pressure and energy that could drive any process, any reaction, any event of any kind has been fully and permanently exhausted. It is a universe in which the laws of physics still apply but have nothing left to act on. A cosmos that has run down so completely that time itself becomes a meaningless concept, because time is only meaningful when things change, and in the final state of maximum entropy, nothing changes anymore, ever. This is the heat death of the universe, also called the Big Freeze, and it is, according to our best current understanding of cosmology and thermodynamics, the most likely fate of everything. To understand the heat death, you need to understand entropy. Entropy is a measure of disorder, or more precisely, a measure of how many different microscopic arrangements a system could be in while still looking the same from the outside. A glass of hot water has lower entropy than a glass of cold water mixed with warm water, because the hot glass has all its energetic molecules concentrated in one place, which is a relatively ordered arrangement. The mixed glass has that energy spread out more evenly, which corresponds to a greater number of possible microscopic arrangements. The second law of thermodynamics, one of the most fundamental principles in all of physics, states that entropy in a closed system always increases or stays the same. It never decreases spontaneously. Order always tends toward disorder. Concentrated energy always tends to spread out. Hot things cool down, mixing with their surroundings until temperature differences disappear. Structured things break apart, their components dispersing until no trace of the original structure remains. This is not just a tendency, it is a law, and the universe, as a whole, is subject to it. Right now, the universe is far from thermal equilibrium. It is full of temperature gradients, pressure differences, and pockets of concentrated energy. Stars burn at millions of degrees while the space around them hovers just above absolute zero. Galactic cores churn with violent activity while the voids between galaxy clusters sit in near-perfect stillness. These differences, these gradients, are what make things happen. They drive the processes of chemistry and biology and geology and everything else. Life itself is a particularly sophisticated way of exploiting energy gradients, of capturing the flow from hot to cold, and using it to build and maintain complex structures temporarily, locally, against the universal tendency toward disorder. But the gradients are being used up. Slowly, over timescales that dwarf the current age of the universe by factors of trillions, every source of usable energy is being depleted, and its energy redistributed into the spreading warmth of equilibrium. Let me walk you through the timeline of the Big Freeze, because the numbers involved are so large they constitute their own kind of poetry. The Sun has about 5 billion years of hydrogen fuel remaining. When it exhausts that fuel, it will expand into a red giant, engulf the inner planets, and eventually shed its outer layers, leaving behind a dense, cooling remnant called a white dwarf. Most stars in the universe will follow similar paths, their timescales varying with their masses. The last low-mass red dwarf stars, the most fuel-efficient stars in the universe, will continue burning for roughly 10 trillion years, 1,000 times the current age of the universe. When the last red dwarf finally exhausts its fuel and fades to a cold, dark cinder, the era of stars will be over. The universe will have entered what cosmologists call the degenerate era, populated by white dwarfs, neutron stars, and black holes, with no new stars forming and no nuclear fires burning anywhere in the cosmos. The degenerate era lasts an almost incomprehensibly long time. White dwarfs cool slowly, radiating their stored heat into the void over timescales of quadrillions of years, eventually fading to cold, dark objects sometimes called black dwarfs. Whether true black dwarfs can actually form within the current age of the universe is debated, because the cooling time required may exceed even the projected lifespan of the universe itself. Meanwhile, even the protons that make up ordinary matter may eventually decay if certain grand unified theories of physics are correct, on timescales of roughly 10 to the power of 34 years. If proton decay occurs, then all the matter that was not consumed by black holes will slowly dissolve, atom by atom, over unimaginable stretches of time, leaving behind only photons and leptons drifting through an expanding, cooling, darkening void. If proton decay does not occur, that same matter persists, but grows colder and darker and more inert with every passing eon. The black holes outlast everything else. They are the last complex structures in the universe, the final repositories of concentrated mass and energy in a cosmos that has otherwise reached near total equilibrium. But even black holes are not eternal. Stephen Hawking showed in 1974 that black holes slowly evaporate, radiating energy in the form of what is now called Hawking radiation, a quantum process by which a black hole very gradually loses mass and eventually disappears entirely. The timescale for this process is staggering. A black hole with the mass of our Sun would take roughly 2 times 10 to the power of 67 years to evaporate. The supermassive black holes at the centres of galaxies, with masses billions of times that of the Sun, would take on the order of 10 to the power of 100 years. These are numbers so large that the current age of the universe, 13.8 billion years, is to them as a single second is to the age of the universe. But they are finite. The black holes will evaporate, and when the last one does, the universe will contain nothing but a thin, cold, uniform gas of photons and elementary particles, spread across a space that is still expanding at a temperature so close to absolute zero as to be indistinguishable from it in any practical sense. This is maximum entropy. This is thermal equilibrium. This is the heat death. A universe in perfect balance, with no gradients left to drive any process, no energy left to do any work, no structures left to change or grow or decay. Not darkness in the dramatic sense, because photons still exist, still travel at the speed of light across the expanding void, but a darkness in the thermodynamic sense, a universe in which nothing happens and nothing can happen, in which the concept of an event has become physically meaningless. Time passes, in the sense that the universe continues to expand, but nothing marks its passage, nothing changes, nothing begins or ends. The universe simply is, in a state of such perfect featureless uniformity that it cannot be distinguished in any physically meaningful way from nothing at all. And yet I find something unexpectedly consoling in this picture, alongside the vertigo it produces. The heat death is not a sudden catastrophe. It is not a violence imposed on the universe from outside. It is the universe completing a process that has been underway since the first instant of the Big Bang, the gradual, patient, law-abiding redistribution of all the concentrated energy released in that first moment into the most spread out, most even, most harmonious configuration possible. It is the universe, in a sense, coming to rest, finding the equilibrium it has been moving toward for every one of its 13.8 billion years. There is something almost graceful about that, something that feels less like an ending and more like an arrival, the universe settling at last into stillness, and the night around you right now, the quiet dark, the slow rhythm of your breathing, is a brief and brilliant and unrepeatable moment somewhere near the very beginning of that long journey toward rest. We have spent a great deal of time together exploring what the expansion of the universe does, how it carries galaxies apart, how it accelerates under the influence of dark energy, how it will eventually thin the cosmos into a cold and featureless void. But there is a deeper question waiting beneath all of that, one that has been sitting quietly at the bottom of everything we have discussed, patient and unresolved and genuinely frightening in the way that only the most fundamental questions can be. Not what does the expansion do, but why does it exist at all? Why is there a cosmological constant? Why does empty space have energy? Why does the universe have the specific physical laws and constants that it has, rather than some other set, and what, if anything, determines those values? These are not questions at the frontier of cosmology in the sense of being almost answered. They are questions at the frontier in the sense of being barely formulated. We are not close to answering them. We are not sure we know how to answer them, and the most honest response physics can currently give to the question of why the universe expands is a response that is either deeply unsatisfying or cosmically terrifying, depending on how you look at it. The answer is, we don't know, and the reason we don't know may be that the question has no answer accessible to us. Let me explain what I mean by that. In physics, when we ask why a constant has the value it has, we are asking for a deeper theory that derives that value from more fundamental principles. Why does the electron have the mass it has? We hope one day for a theory that predicts it. Why does the speed of light have the value it has? Perhaps a future framework will show that value to be necessary, derivable from something more basic. This is the normal scientific expectation, that the constants of nature, the numbers that appear in our equations, are not arbitrary, but are determined by some deeper structure we have not yet uncovered. But dark energy, the cosmological constant, resists this approach in a particularly stubborn way. When we try to derive its value from our best fundamental theories, we get that catastrophic disagreement by a factor of 10 to the power of 120 that we discussed earlier. Our deepest theories give us the wrong answer by the largest margin in the history of science, and the correct answer, the tiny residual value we actually observe, has no explanation from first principles that anyone has been able to construct. One proposed explanation is deeply controversial and deeply strange. It is called the anthropic principle, and in its most provocative form it goes something like this. Suppose the cosmological constant is not determined by any fundamental law. Suppose it is, in some sense, random. Suppose there are a vast number of universes, perhaps an incomprehensibly vast number, each with different values of the cosmological constant and different settings for all the other constants of nature. A multiverse in the technical sense. Most of those universes would have cosmological constants, either so large and positive that space would expand so rapidly that no structures could ever form, no galaxies, no stars, no planets, no chemistry, no life. Or so large and negative that the universe would collapse back on itself in a fraction of a second before anything interesting could happen. Only universes with a cosmological constant in a very narrow range, small enough to allow structure to form but not so small as to cause rapid recollapse, would ever contain observers. We find ourselves in a universe with a small cosmological constant, not because physics requires it, but because we could only exist in a universe where it is small. The observation selects the universe. The universe does not explain itself. This is the anthropic argument, and it makes many physicists deeply uncomfortable. Not because it is logically invalid, it is in fact logically coherent, but because it feels like a surrender. It says that the most important number in cosmology, the number that determines the ultimate fate of everything, has the value it has because if it were different, we would not be here to notice. It replaces a physical explanation with a selection effect. It answers the deepest why in science with a shrug dressed in mathematics. And yet, uncomfortable as it is, it may be correct. The multiverse picture arises naturally from the leading framework for understanding the very early universe, a theory called eternal inflation, in which the Big Bang was not a unique event, but one of an endless number of inflationary episodes, each spawning a new region of space-time with its own randomly determined physical constants. If eternal inflation is correct, the multiverse is not a speculation, it is a prediction, and the anthropic selection of our particular set of constants follows naturally from it. Here is the thing most people do not realize about the multiverse explanation. It is not testable in any direct sense. By definition, other universes in the multiverse are beyond our cosmic horizon, beyond any possible observation, beyond any causal contact with our own universe. We cannot send a probe there. We cannot receive a signal from there. We cannot, in principle, ever verify that they exist. This places the multiverse in an uncomfortable position scientifically, somewhere between a genuine physical theory and a philosophical framework. Some physicists regard it as the most likely explanation for the values of our constants. Others regard it as unscientific precisely because it cannot be tested. The debate is active and unresolved and unlikely to be settled by any observation we can currently imagine making. We are, in this respect, genuinely at the edge of what science can reach. But let us sit with the full weight of what the anthropic argument implies, because I think it deserves more than a quick dismissal or a quick acceptance. It implies that the universe we inhabit is not special in any fundamental physical sense. It is one sample from a distribution of possible universes, selected for our presence rather than for any deeper reason. The stars, the galaxies, the planets, the chemistry, the biology, the consciousness that enables you to lie here and wonder about all of this, none of it was inevitable. None of it was the point. It is all a consequence of a random draw that happened to fall in the habitable range. The universe did not intend to produce complexity or life or minds. It simply happened to have constants compatible with their existence. And in an ensemble of all possible universes, the ones compatible with observers are the ones that get observed. We are the selection bias made conscious. We are the universe noticing that it drew a lucky number. And here is where the terrifying and the beautiful become impossible to separate, because that same lucky draw, that same improbable configuration of constants, produced everything, every star that has ever burned, every planet that has ever orbited, every ocean that has ever reflected the light of its sun, every mind that has ever looked up and wondered. The expansion of the universe driven by a cosmological constant, whose value we cannot explain from first principles, proceeding at a rate that happens to be compatible with the formation of structure and the emergence of life, is the reason any of this exists. Change the cosmological constant by a tiny fraction in either direction, and the universe is sterile. No galaxies, no stars, no you. The value that drives the expansion also permits the existence of everything that is aware of the expansion. The most terrifying number in physics is also the most generous. It is the number that made room for all of this, for the night sky and the questions it raises. For you, lying here in the dark, wondering why, there is a reframing available to us, one that I want to offer gently, because I think it changes something important about how the expansion of the universe feels when you sit with it in the dark. We have been talking about the expansion largely in terms of loss, galaxies receding, horizons closing, evidence erasing, futures growing cold and empty, and all of that is true. But there is another way to read the same data, a way that does not deny any of it, but places it in a context that makes it feel less like a slow catastrophe and more like an extraordinary privilege. We happen to exist at the one moment in the entire history of the universe when the cosmos is fully, gloriously, unrepeatable alive. Not alive in the biological sense, though it is that too, briefly, locally, miraculously. Alive in the astronomical sense. Burning, structured, populated. Lit from within by hundreds of billions of galaxies, each containing hundreds of billions of stars, each star a furnace of nuclear fire converting hydrogen into heavier elements and releasing light that travels for millions of years through the expanding dark. This moment, this era, this epoch of stars and galaxies and planets and curious minds is cosmically unique. It has never existed before in this form. It will never exist again. We are, without question, living in the golden age of the cosmos. To appreciate what that means, you need to hold the full timeline of the universe in your mind, not just the past but the future, and notice where we are situated within it. The universe is 13.8 billion years old. The last low-mass stars are expected to burn for roughly 10 trillion years, which is about 700 times longer than the universe has currently existed. After that, the era of stars ends and the long, dark, cooling, degenerate era begins, lasting incomprehensibly longer still. If you were to compress the entire projected lifespan of the stelliferous era, the period of star formation and burning, into a single calendar year, the current age of the universe would correspond to roughly the first week of January. We are at the very beginning of the age of stars, not at its peak, not past it, but near its opening chapter. And yet even this early moment, this first week of the cosmic year, is already rich beyond any adequate description. The universe has produced 2 trillion galaxies, each one a city of stars, each city populated with worlds. All of that complexity and structure and light exists right now, tonight, surrounding you in every direction. But here is the detail that I find most affecting. The era of stars, for all its duration, is not the dominant era of the universe's total lifespan. It is a brief bright interval in a much longer story that is mostly dark. The stelliferous era, 10 trillion years of starlight, is followed by the degenerate era, and then the black hole era, and then the dark era, each one vastly longer than the last, each one darker and emptier and less eventful than the one before. The total lifespan of the universe, if we measure it to the evaporation of the last black hole, stretches to timescales written as 10 to the power of 100 years and beyond. Against that backdrop, the era of stars is not long. It is a spark, a brief, brilliant, improbable flare of light and heat and complexity in a timeline that is otherwise dominated by cold and dark and stillness. And we are inside that spark. We were born inside it. We are made of it. The light of burning stars, the chemistry of stellar nucleosynthesis, the warmth of a sun 93 million miles away, these are not the background conditions of the universe. They are the temporary, precious, unrepeatable conditions of a very specific and very fortunate moment. Think about what was required to produce this moment. The Big Bang created hydrogen and helium. Nothing more, no carbon, no oxygen, no nitrogen, no iron, no phosphorus, none of the elements that biology requires. Those elements had to be forged inside stars, built up through billions of years of nuclear fusion, and then scattered across space through supernova explosions so that future generations of stars could incorporate them into new solar systems with rocky planets. The Sun is a third-generation star. Its heavy elements were produced inside at least 2 previous generations of stars that lived and died before the solar system existed. The calcium in your bones was forged in a stellar explosion that happened before the Earth was born. The iron in your blood was produced in the core of a star that no longer exists. You're not just living in the golden age of the cosmos. You are built from the accumulated work of that golden age, assembled from the debris of stellar lives that spanned billions of years before yours began. Here is the thing most people do not realize about the timing of our existence. We are not just fortunate to be alive during the era of stars. We are fortunate to be alive at the particular moment when the universe has had enough time to produce the chemical complexity that biology requires, but has not yet aged so far that the conditions for life have degraded. In the very early universe, in the first billion years, there were stars, but they were mostly large, fast-burning, and poor in heavy elements. The conditions for rocky planets with complex chemistry did not yet exist. Life as we know it was not yet possible. Now, 13.8 billion years in, the universe has had enough time to build up the necessary chemical inventory through multiple generations of star formation and stellar death. The raw materials are available, the conditions are right. And they will remain right for a very long time, for billions of years more, as the universe's remaining stars continue to burn and seed their neighborhoods with the elements of possibility. But that window is not infinite. Eventually, the rate of star formation will decline. The raw material for new stars, the cold gas clouds that collapse under gravity to form stellar nurseries, will be consumed or dispersed. The universe will age. The stellar fires will dim one by one. The chemical enrichment of space will slow and then stop. And the conditions that make life possible, the particular combination of energy availability and chemical complexity, and stable planetary environments, will become progressively rarer and eventually impossible. We are not at the end of that window. But we can see it from here in the sense that we understand the process well enough to know that it has limits. The Golden Age is long but not eternal, and knowing that, feeling that, changes the quality of the light outside your window in a way that is hard to articulate but easy to feel. There is a word I keep returning to when I think about all of this, and the word is gratitude. Not gratitude directed at anything in particular, not a theological claim, but a felt response to the simple fact of being here, now, in this unrepeatable moment of cosmic history. The universe has been running for nearly 14 billion years, and will continue running for timescales that make that number look like a rounding error. And in the middle of all that time, on a small rocky planet orbiting an ordinary star in one of 2 trillion galaxies, at the particular moment when the chemistry of stellar evolution had produced enough complexity for biology to emerge and for minds to develop, and for consciousness to look up at the night sky and wonder what it means, you exist. You are here. Tonight is real. The questions are real. The astonishment is real. The universe produced it all. blindly through the patient operation of physical laws across billions of years. And the result tonight, right now, is this: you, awake to wonder, inside the golden age, floating in the expanding dark. On Christmas Day of 2021, a rocket lifted off from a launch site on the northeastern coast of South America and carried into space the most complex and expensive scientific instrument ever built by human hands. The James Webb Space Telescope, the product of more than 2 decades of engineering work, the collaboration of thousands of scientists and engineers across multiple countries, and a total investment of roughly $10 billion, folded itself into a rocket fairing like an origami flower and began a month-long journey to its operating position, a gravitationally stable point in space roughly 1 million miles from Earth. Over the following months it unfolded, cooled, aligned its 18 hexagonal gold-coated mirror segments to nanometer precision, and began looking at the universe with a sensitivity and resolution that made every telescope that came before it seem, by comparison, like a human eye squinting in a dim room. What it has seen since then, in just a few years of operation, has already forced astronomers to revise some of their most confident assumptions about the early universe, and it has done so in a way that connects directly and viscerally to everything we have been exploring tonight. The James Webb Space Telescope was designed to see further back in time than any instrument before it. Its predecessor, the Hubble Space Telescope, had already shown us galaxies from roughly 13 billion years ago, when the universe was less than 1 billion years old. Webb was built to push that boundary further into the first few 100 million years of cosmic history, the epoch sometimes called Cosmic Dawn, when the very first stars and galaxies were switching on in a universe that had been dark since the fog of the early plasma cleared. To do this, Webb observes primarily in infrared light. The ancient light from those early galaxies has been travelling for so long, across such vast expanding distances, that its wavelengths have been stretched by the expansion of space from ultraviolet and visible light all the way into the infrared, far beyond what human eyes or even Hubble's instruments can detect. Webb sees in the wavelengths of that ancient redshifted light. It is, in a very literal sense, a machine designed to look across the expansion and read what the universe wrote in its earliest chapters. The first deep-field images from Webb arrived in July of 2022, and the scientific community's response ranged from awe to genuine perplexity. The images were breathtaking in the way that deep-field images always are. Thousands of galaxies visible in a patch of sky no larger than a grain of sand held at arm's length. Each one a complete island universe of billions of stars, each one shown to us at a different point in the past depending on its distance. But beyond the beauty, the data contained something unexpected. In the very early universe, in the first few 100 million years after the Big Bang, Webb found galaxies that were far more massive, far more structured, and far more chemically evolved than the prevailing models of galaxy formation had predicted. Galaxies that should, according to those models, have still been in the early stages of assembly, small and irregular and thin on heavy elements, appeared instead as large, organised, mature systems, with substantial stellar populations already in place. One set of observations was particularly striking. Webb identified a population of galaxies from when the universe was only 400 to 700 million years old, a tiny fraction of its current age, that appeared to contain as many stars as the Milky Way contains today. This should not have been possible under the standard model of galaxy formation, which describes galaxies growing gradually through the mergers of smaller structures over billions of years. You cannot build a Milky Way in 400 million years, the model said. The physics of gravitational collapse and star formation simply does not work that fast. And yet Webb's data showed what it showed. Massive, structured galaxies in an infant universe, staring back at us across 13 plus billion years of cosmic expansion, asking questions that our best theories of structure formation are still working hard to answer. Here is the thing most people do not realize about what this means for our understanding of the expansion. The expansion of the universe is not just the backdrop against which galaxy formation occurs, it is an active participant in that process. The rate of expansion in the early universe, driven initially by the energy of the Big Bang, and then gradually slowing under the influence of gravity and radiation pressure, determined how quickly matter could clump together under gravity to form the first structures. Too fast an expansion and matter would have been dispersed before it could collapse into anything. Too slow, and the universe would have recollapsed before stars could form. The expansion rate in the early universe had to fall within a specific range for structure to form at all, and the structures Webb is revealing suggests that either the expansion in those early epochs was slightly different from what our models assume, or that some other physics, some mechanism we have not fully accounted for, was accelerating the formation of large structures in the first billion years. Webb has also been examining the epoch of reionization, the period when the first stars and galaxies began pouring ultraviolet radiation into the surrounding hydrogen gas of the early universe, gradually ionizing it and making the cosmos transparent in a way different from the earlier recombination epoch we discussed. This process was expected to be gradual, spread over hundreds of millions of years, driven by the slow accumulation of stellar radiation from early galaxies. Webb's observations suggest it may have proceeded more quickly and been driven by a somewhat different mix of sources than expected. The early universe, it appears, was a more energetic and rapidly evolving place than our models had allowed for. It was not a gentle, slow awakening from cosmic dark, but something more vigorous, more efficient, more surprising. The expansion created the stage, but the first performers arrived earlier and played louder than the script called for. What I find most moving about the Webb telescope, beyond the scientific results, is what it represents as an act of human intention. We built a machine, with enormous difficulty and expense and time, specifically to look at the oldest light in the universe, to reach across the expansion, across 13 billion years of stretching space, and read the handwriting of the cosmos in its infancy. We did this not because it was economically profitable or strategically useful. We did it because we wanted to know. Because the question of where we came from, how the universe assembled itself from the hot uniformity of the Big Bang into the structured complexity of today, is a question that matters to us in some way that transcends utility. It matters because we are inside the story and we want to understand it. The James Webb Space Telescope is the universe using the biology it produced, on a small rocky planet in an expanding cosmos, to look back at its own origin. It is a mirror aimed at the beginning of time, held up by creatures who would not exist without the 13 billion years of expansion that separate them from the light they are trying to read. Every image Webb sends back is a message from before we existed, carried across the expansion by light that was already ancient when the Earth formed. It shows us a universe that was actively building itself, assembling the ingredients that would eventually, improbably, produce the world you are lying in tonight. The galaxies Webb sees at the edge of the observable universe are not distant and irrelevant. They are ancestral. They are the early chapters of the story that ends here, with you breathing quietly in the dark, aware that you are made of the universe's own accumulated history, and that somewhere, in the gold-coated mirrors of a telescope a million miles from home, that history is still being read. We have travelled a long way together tonight, from the cold hook of an expanding cosmos to the quantum seething of empty space, from Edwin Hubble's Mountain Observatory to the gold-coated mirrors of the James Webb Space Telescope, drifting a million miles from home, from the first fraction of a second after the Big Bang, to the last evaporating black hole in a universe of perfect, featureless cold. We have sat with the acceleration that no one predicted, and the dark energy that no one can explain. We have watched galaxies vanish across the cosmic horizon and imagined future civilizations born into a sky stripped of every neighbour, every signal, every trace of the vast and luminous universe that once surrounded them. We have looked at two possible endings, one violent and one quiet, and found in both of them something that is simultaneously terrifying and in its own strange way complete. And now, in this final chapter, I want to pull back one more time, further than we have pulled back before, and look at the whole picture from the greatest distance available to us. Not a distance in space, a distance in perspective. I want to look at what it means that any of this is known at all. The universe is approximately 13.8 billion years old. For the overwhelming majority of that time, nothing in it was aware of it. The Big Bang happened in the absence of any witness. The first stars ignited in a universe with no one to see them. Galaxies assembled and collided and merged across billions of years of cosmic history that left no record in any mind, because no minds existed. The heavy elements were forged in stellar interiors and scattered across space in supernova explosions that lit up regions of the cosmos with no eyes to receive their light. Planets formed, oceans pooled, chemistry grew complex, and then, on at least one small rocky world, orbiting an ordinary star in the outer spiral arm of an unremarkable galaxy, something happened that had never happened anywhere before in those 13+ billion years of cosmic history. Matter became aware of itself. The universe produced from its own substance, through the patient operation of its own physical laws, something capable of asking where it came from. This is not a small thing. It is, I would argue, the most astonishing fact in the entire story we have told tonight, more astonishing than the scale of the expansion, more astonishing than the mystery of dark energy, more astonishing than the incomprehensible timescales of the deep future, because the expansion and the dark energy and the deep future are facts about the universe. But the awareness of those facts, the capacity to discover them, to measure them, to be troubled by them, to lie awake at night wondering about them, that is something the universe did to itself. You're not separate from the expanding cosmos, looking at it from outside. You are made of it. You are a local configuration of its atoms, a temporary arrangement of the hydrogen and carbon and oxygen and nitrogen that the universe assembled through 13.8 billion years of stellar alchemy. And in that arrangement, somehow, awareness arose. The cosmos produced eyes and then looked through them. It produced minds and then thought with them. It produced the question and then asked it of itself. The physicist Carl Sagan expressed this with a simplicity that has never been improved upon. We are a way for the cosmos to know itself. That sentence is worth dwelling on slowly, in the quiet. Not as a metaphor, not as poetry, though it is that too, is as a literal description of what is happening when you lie here in the dark and think about the universe. The carbon in your body was forged inside a star. The iron in your blood was produced in a stellar explosion. The water in your cells has been cycling through the Earth's systems for billions of years, and through the cosmos for longer still. Every atom that makes you up was, at some point in the universe's history, part of something else. A star, a nebula, an ancient ocean, a different living thing. And now those atoms are arranged in a way that generates consciousness, that produces the experience of wondering, that makes possible the very question of why the universe expands. The expansion created the conditions for stars. The stars created the atoms, given time and the right conditions, created you. And you, tonight, are completing a circuit that began at the Big Bang. Here is what I find most quietly extraordinary about this. The universe did not have to do this. There is nothing in the laws of physics that required it to produce consciousness. The laws of physics required atoms to form and stars to burn and galaxies to assemble, but awareness is not written into those equations. It is an emergent property, something that arose from the complexity of the universe's own workings without being explicitly demanded by its fundamental rules. And yet it arose. Here, at least on this planet, at this moment in cosmic history, the universe became aware. It began to notice itself, and in noticing itself, it made all the difference. Because a universe that is not observed, that contains no awareness of any kind, is in some profound sense incomplete. Not physically. The expansion would proceed just the same. The dark energy would push just as relentlessly. The galaxies would recede just as inevitably. But it would all be happening in the dark, unremarked, unwitnessed, generating no meaning because there would be no one to receive meaning from it. We are what gives the universe's story an audience. We are how it becomes, in any sense that matters to us, a story at all. And so we arrive at the place where the terrifying and the beautiful finally resolve into each other. Yes, the universe is expanding. Yes, it is accelerating. Yes, the galaxies are receding. The horizons are closing. The evidence of our cosmic history is being slowly erased. And the ultimate fate of everything is either a violent rip or a quiet freeze extending across timescales that make the current age of the universe look like a single breath. All of that is true, and it is genuinely terrifying in the way that all truly large things are terrifying when you look at them directly without flinching. But it is also the same universe that produced the conditions for stars, and stars produced the conditions for planets, and planets produced the conditions for oceans, and oceans produced the conditions for life, and life produced the conditions for minds, and minds produced the capacity to understand all of the above. The same expansion that will eventually erase every galaxy from our sky first created the room for them to exist. the same dark energy that will one day leave the cosmos cold and empty first, held it open long enough for everything we have ever known to come into being. The universe is not indifferent to us in the way a stone is indifferent. It made us. We are its most recent and most improbable expression. We are the universe noticing itself and finding, against all odds, that there is something worth noticing. Thank you for staying with me through all of it tonight, through the expansions and the horizons and the endings and the beginnings, through the quantum vacuum and the dying stars and the deep field images of galaxies older than the Earth. It means something to me, genuinely, that you chose to spend these hours wondering about the cosmos rather than anything else. If you found something in tonight's journey that moved you or stayed with you, please take a moment to like or subscribe. It is a small gesture that helps this channel reach more curious minds who might be lying awake somewhere in the dark, looking for exactly this kind of company. And now, before you sleep, one last thought to carry with you. The next time you step outside on a clear night and look up at the stars, remember that every photon of light reaching your eyes has made a journey of years or centuries or millions of years through the expanding universe to arrive at that precise moment, at that precise place, at you. The universe has been expanding for nearly 14 billion years, carrying everything with it, building complexity from simplicity, producing from hydrogen and time and the patient operation of physical law everything that exists, including the mind that is now aware of all of it. You are not small in comparison to the universe. You are the part of the universe that knows how large it is. That is not nothing. That is everything. Sleep well tonight, and keep looking up at the stars.